Yes. For a test, I can make the geometry easier to figure out, you know. But I can't condense it too much, so yeah, I just can't ask very many questions, you know. Yeah, definitely less than like 20 members. Okay, so we have 7 equations, 7 variables, so that means 8 columns. Seven rows. And I set up the variables like f12x, f12y, alpha 1, r, acom 2x, acom 2y, alpha 2, and then the constants. Equation 1, 2, 3, 4, 5, 6, 7. Yep. That's true. I guess in case you were going back through for it later, maybe. So I'll just fill in the non-zero values. So 1.03, negative 2.81, negative 30, and then negative 756.3. Equation 2, negative 1 for f12x, negative 1 for r, negative 10 for center of mass x. Equation 3, negative 1 for y, for f12y, negative 10 for center of mass y, 98.1 for the constant. Equation 4 is 0.51, 1.41, negative 0.51 for center of mass x, negative 7.5 for alpha 2. And now the constraint equations. Equation 5 says 1.03 alpha 1 minus 1 center of mass x, 0.51 center of mass 2, alpha 2. Equation 6 says negative 2.81 alpha 1, negative 1 center of mass y, 1.41 alpha 2. And then the last one says 1 for center of mass x, 0.51 for alpha 2, and then 0. And the answers I got are F12 is negative 230.1 newtons, 127.8 newtons. R is equal to 202.6 newtons. The acceleration of the center of mass of 2 is equal to 2.75 meters per second squared, negative 22.6 meters per second squared. And then the angular accelerations, alpha 1 is equal to 5.34. Alpha 2, which I said we expect to be equal and opposite, I got negative 5.39, which is just round off error. Those are equal and opposite because the triangle has to stay isosceles. All right, so none of those were the question. The question was, what's the acceleration vector at the point C? So how do we figure that out now? Yeah, so, well, the acceleration at c is relative to the ground is equal to the acceleration of c relative to the center of mass of 2 plus the acceleration of the center of mass of 2 relative to the ground. This one is this, so that's good, that's easy. This one is from the watermelon equation. I have one question here. Why am I doing the acceleration? Oh, so let me set up this watermelon equation, and then maybe my question will make sense. So the acceleration of c is equal to alpha 2 crossed with the r vector from the r vector to the point c from the center of mass of 2 plus 0, because we don't have any angular velocities in this case. Plus 2.75 negative 22.6. Why am I setting this equation up in terms of body 2 instead of body 1? Like, but we have the fixed point on 1. We could just do it about the fixed point. So what's the for c? That's right, and it's on member 2. So remember, all of these equations only hold for a rigid body, you know. So we can't talk about the relation, use these equations to look at the relationship between the point C and a rigid body that it's not a part of, you know. All right, so alpha 2 is 0, 0, negative 5.39. That r vector, we've already done that one. That is 1.41. Negative 0.51, 0, plus 2.75, negative 22.6, 0. I guess I'll do that one. Race me. Done. So I got 0.0011 negative 30.1999. This is obviously round off error. We required that acceleration couldn't be anything, and negative 30.2 for the y acceleration.
So why wouldn't you have just used the equation and solve for?
Yeah, in this case, that would have been fine. The way I'm in the habit of doing it is I do what I think of as solving the problem. I get those accelerations and those angular accelerations. And then while I'm doing that, I'm not even thinking about what it asked for. And then I go back afterwards and use those to figure out what I'm asked for.
the acceleration due to gravity is already in calculation.
Well, so there's no, I guess the way I think of it is like there's no acceleration due to gravity. Gravity applies a force, and if the thing is in free fall, or then that creates a certain acceleration. So those forces due to gravity are included. There's no actual acceleration that has to come from gravity. You know, like things can be static, but so that's how I think of it. Like gravity doesn't really cause an acceleration; it causes a force. And if there's not something there to restrict that force, then an acceleration follows, you know. Any other questions about that? So yeah, these are long problems. What? Yeah, one or two of these, that's all I can do, you know, on a test. So. Okay, so now we're moving on. Unless anyone else has anything they'd like to complain about. Matt, anything? Okay. You don't like the way I solved it? Okay. I'll keep that in mind for next time. All right. So now we're moving on to, I think, kind of the hairiest and the coolest topic in dynamics. That is, well, for us, we're just doing particle kinematics and particle kinetics. That part's not so cool. Kinematics, kinetics, but that's sort of beside the point. The real, the important thing is in non-inertial coordinate systems. All right, there are two ways that a coordinate system can be non-inertial. What are they? The origin accelerating. And the second one? The axes are rotating, yep. This one is, there's nothing left that I really have to say about this. You deal with the origin accelerating with the relative motion equations. Okay, that makes sense. Like, if you know what the acceleration of the origin is, you use the relative motion equations to add that on to whatever acceleration you've measured in the coordinate system. So this is easy. I mean, compared to the other one. You just use the relative motion equations. And I guess if we're talking about acceleration, you just use the acceleration of p relative to the ground is equal to the acceleration of p relative to a plus the acceleration of a relative to the ground. And that's it. This one is harder. And so this is what we're going to spend our time on. Although I'm going to throw some problems like this in there. You know, we'll mix it in. But okay, so both of these, I mean, you want something to hang your hat on for these. These are what's happening to the camera in the Jamiroquai video, right? That's what I showed. Also, someone wrote this on their test and misspelled Jamiroquai. Actually, I don't really know how to spell it. Jamiroquai? Aquai? Something like that. That looks okay. I'm just going with the odds. I'm playing the percentages. There's so many ways you could misspell it. I'm sure they probably did. Oh, I thought about O there. Everything else is right, right? No U? Okay, got it. All right, so what's the problem with, so what goes wrong when you have a rotating coordinate system? In a way, in a way it's sort of strange. Like, this makes sense. Like, yeah, if your coordinate system is adding acceleration onto what you're measuring, that's going to mess up Newton's second law, right? This one makes sense. What goes wrong here when the axes are rotating? Well, it's actually a property of taking the derivatives. And it's kind of, I think it's hopefully kind of helpful. I think it's kind of interesting to see how this works. So what goes wrong? When the axes are rotating? Well, in a non-rotating coordinate system, think about taking the time derivative of a vector. It doesn't matter what vector it is. Of just some arbitrary vector u. Okay, so u dot is, how do you calculate that? If the vector u is made up of ux, uy, uz, then the time derivative is just the time derivatives of the components. Oops. Another way of writing this, the way, like, you probably saw this notation in physics at least, is the time derivative of u is equal to ux dot times I plus uy dot times j plus uz dot times k, right? But that seems to sort of gloss over, doesn't take the product rule into effect. So now if you're taking a time derivative of, so our vector u, let's think of the vector u as ux times I plus uy times j plus uz times k. When you take that derivative, what you should get is ux dot I. That part's the same as up here. But now what? For using the product rule. Well, we're still on this one because of the product rule. You know what I mean? So you have ux times I dot. Right? And now move on to to the time derivative of this term, and you get uy dot j. That makes sense with this, but then the product rule says we also have to have uy times j dot. And then move on to the derivative of the third term. You have uz dot times k. We have that one up here. Plus uz times k dot. And this term, and this term screw everything up. So I mean, notice that if the coordinate axes aren't changing directions, there's no time derivative of I, j, or k, right? But if these are rotating, then these are changing. So when I dot isn't equal to 0, or j dot isn't equal to 0, or k dot isn't equal to 0. Okay, so that's right. That's right. That's right. Those aren't just constant vectors. They change in time, and so they have time derivatives. And so everything gets complicated then. So when the axes aren't rotating, this sort of shorthand way of, this abbreviated way of taking time derivatives of vectors, that works fine because these terms go away. This is 0, this is 0, and this is 0. But if those axes are changing, you have to take these terms into account. So I want to I think this is kind of a helpful way of thinking about this. So it's not just I guess to me, like, this isn't something it's some abstract mathematical thing. You can actually sort of wrap your head around what problems this creates. The way I think it helps to think about this is, imagine one of those astronaut training things that they always do in Popeye and stuff, where they put you in a chair and spin you around. Yeah, it's like to test how many G's you can take. Homer Simpson did this. Oh, actually, I think that's why I thought Popeye, because have you seen that episode? It's like the best Simpsons ever. And he turns into Popeye in the centrifuge. Okay, so you're sitting, or the astronaut is sitting here. And this thing is spinning around in a circular path. Okay. And you can build up really high accelerations because you have you can get a pretty big velocity and you have a relatively small distance to the center. So you have a big centripetal acceleration. And let's imagine that, okay, so we could use this to test out Newton's second law, right? Put 4 sensors in the chair, load cells or whatever. And you can use that to measure the total force on the person. And then if you have a camera that's fixed to the ground over here, Okay, the coordinate system's fixed to this camera, so that's the y-axis. X-axis is coming out of the page. Z-axis is going this way. Okay, so based on that, as time goes by, let's call this camera A. Okay. And we're going to set up another camera that rotates with the chair, called camera B. And let's think about what these cameras see in just a few frames as the person goes whizzing by this spot, okay? Because of the extreme pressure. That's what causes the whizzing. No, not really. I'm just talking about the person moving by that spot. So camera A. Let's say that this radius here is 5 meters. Okay. So let's say we're looking at 3 frames of video. The first frame, camera A would see, so what we'd have, so the y-axis is like this, okay? The z-axis is into the page. The x-axis is like this. And the camera would see the person just coming into the frame, right? Like the frame right before they get to this location. This is what the camera sees now. Okay, so we're trying to sort of put ourselves in the frame of reference of this camera. So now Z is going into the page. The second frame has the person right at the, exactly 5 meters in the Z direction from the origin. And then the third frame, the person's gone by. And so the camera just sees this. Okay. And based on these measurements, you could measure the velocity is equal to, the position. So if this is frame 1, frame 2, frame 3, the velocity you could think of as the position at frame 3 minus the position at frame 1 divided by 2 times whatever the time is between frames, right? You could do that. You could do that for every frame and then do it again to approximate the acceleration, and you'd get the velocity at frame, 3 minus the velocity at frame 1 divided by 2 times the elapsed time between frames. And you'd get a good non-zero estimate of the acceleration. Okay. So that works fine. That's for the camera that's fixed in the room and is seeing this guy zip by. Okay. So now think of what this camera B would see that's rotating with the person. So here, there's the y-axis, there's the z-axis. Before the person gets to this position, like the instant before the person gets to that position, the camera's looking right at him, just in another spot, right? So the camera sees this. Yeah, thanks. Okay. Then at the second frame, now the person's gotten to that spot. The camera still just sees the person sitting right there. Now the person goes by the spot. And the camera sees that. So the position in the coordinate system rotating with the person. So what's that position vector of the person? At frame 1, it's just positive 5 in the z direction, right? 0, 0, 5. Here, position 2, 0, 0, 5. Here, position 3, 0, 0, 5. And so now when you take the velocity, yeah, you get 0, 0, 5 minus 0, 0, 5 divided by 2 times the elapsed time. And so it looks like the person isn't moving at all. And now, you know, obviously if you use that to approximate the acceleration, for the same reason, you get an acceleration that's equal to 0. So it looks like this person has no acceleration, while at the same time the force sensors in the chair are telling you that there are big forces being applied to the person. So the force vectors aren't equal to the mass times the 0 vector. And so it appears that Newton's second law doesn't hold. Okay? And if so, mathematically, when I talked about what happens with the derivatives, we can see that it comes from the product rule. Physically thinking about it, you can see the problem with the derivatives comes from the fact that there's changes in time that are being either added on or subtracted off of the true motion by the motion of the camera, you know? So these are the physical and the mathematical side of the same thing. The reason that we have to deal differently with rotating coordinate systems. Okay. Let me let me just introduce this one equation. It'll be fast, and then I'll talk about applying that to things tomorrow. So in a rotating coordinate system, we need to correct our measured time derivatives. So in a rotating coordinate system, our corrected way of calculating u dot for a general vector u is that u dot is equal to the apparent time derivative in the rotating coordinate system. So that's where you just take the time derivatives of the components, like I did in this case. Ux dot, uy dot, uz dot, plus capital Omega crossed with the u vector, where this capital Omega, so this is the angular velocity of the coordinate system. And all of this together you can think of as the correction term. This is the observed or apparent time derivative in the rotating coordinate system. Then you just take it again and you'd have to, and that's what we're going to do to come up with acceleration. Because of the product rule, we're going to have all these cross terms, so you get multiple terms when you do this multiple times. But we'll see how to apply this, and we'll also, like, I think you've probably in physics briefly talked about polar coordinates, like time derivatives using polar coordinates, and you remember you have those really funky expressions, like the, what is it, I always forget them, but the velocity vector is r dot er plus r theta dot e theta. Does that sort of ring a bell? Well, we'll be able to derive that using this equation. Okay.